Late in the evening of May 22nd, 2026, residents across Hawaii's Big Island were jolted by a magnitude 6.0 earthquake that struck deep beneath the island's volcanic foundations. The quake occurred at approximately 10 o'clock at night Hawaii Standard Time, with an epicenter just south of the town of Honaunaunipopu, roughly 13 kilometers, 8 miles away. But what immediately caught the attention of seismologists was not simply the magnitude. It was the depth. The rupture originated about 22 kilometers, approximately 14 miles, beneath the surface, far below the shallow magma plumbing systems normally associated with Hawaiian volcanic earthquakes. What kind of fault slips that deep beneath a shield volcano? Why did the rupture carry such a strong compressional signature? And could this event be part of a much larger structural process unfolding beneath Hawaii itself, one that resembles the geological conditions preceding the devastating 1975 Kalapana earthquake and parts of the 1868 Hawaii earthquake sequence? Analysis of the seismic data, particularly the moment tensor solution, makes it clear that the tremor involved a reverse oblique slip on a deep subhorizontal fault. In practical terms, this means the rock on one side of the fault was thrust up and over the other side, with a significant sideways component as well. The focal mechanism gives two possible fault planes: one steep plane with strike 189 degrees, dip 64 degrees, rake 70 degrees, and one shallow plane with strike 49 degrees, dip 33 degrees, rake 125 degrees. Both solutions show a strong compressional character, meaning thrusting, but the slightly more shallow plane with dip 33 degrees better matches what we know about the hidden fault geometry under Hawaii. In fact, global centroid moment tensor data for Hawaii show that events of magnitude 5 or larger almost invariably involve a shallow, gently dipping thrust fault below the volcano flanks. In short, the mechanism, a dominantly reverse thrust motion with some horizontal slip, is exactly what one would expect if the south flank of Hawaii is letting go along its basal detachment. But what is this detachment? In volcanic islands like Hawaii, thick layers of lava and volcanic debris rest atop much older oceanic crust. Between these two distinct layers lies a weak zone, a buried nearly horizontal fault, along which the entire volcanic pile can slide seaward under its own weight. Geologists call this the basal detachment, from French décoller, meaning to detach. It typically sits at roughly 10 to 11 kilometers depth beneath the surface, about 6 to 7 miles. In the words of United States Geological Survey scientists, the most destructive earthquakes in Hawaii occur along a gently sloping fault between the base of the volcanoes and the ancient ocean floor on which they are built. This fault, located at a depth of approximately 11 kilometers, about 7 miles, is known geologically as a detachment. Slip on this detachment has been implicated in every major Hawaii quake of the last 2 centuries. All the evidence points to this deep detachment as the culprit for the May 22, 2026 tremor. Its depth of about 22 kilometers, about 14 miles, is well below the volcano summit and rift zones, and far below any shallow magma conduits. Instead, it lies squarely in the zone where the hot volcanic rock meets and rides over much older, cooler crust. In Hawaii, rock gets gradually stronger with depth until about 6 to 10 kilometers, about 4 to 6 miles, then becomes more ductile again. The detachment sits near that brittle ductile transition. An earthquake there is not a volcanic eruption at all, but a readjustment of the flanks under their own weight. This picture is reinforced by the historical pattern. Scientists have long known that Hawaii large quakes, including the famed 1975 Kalapana event and the great 1868 Hawaii quake sequence, occurred on this basal slip surface. The recent United States Geological Survey Volcano Watch newsletter reminds us that a magnitude 7.7 earthquake on November 29, 1975, the Kalapana quake, happened on the same detachment fault. That quake, centered further east on the island, involved massive thrust slip offshore and even generated a tsunami. In fact, experts note that the 1975 rupture was more complicated than a simple single fault slip. Seismic and global positioning system data showed offsets on both the deep detachment and on the shallower Helena fault system, which formed surface scarps along the cliffs. Nonetheless, the detachment was the main actor. Similarly, the Great Kau quake of April 2, 1868, estimated magnitude about 7.9, was also caused by rupture on the basal detachment about 10 kilometers down, about 6 miles. In that case, eyewitness reports of widespread ground slides and tsunamis are consistent with the idea that a huge block of land, the south flank of the island, slid seaward along the detachment. It may seem counterintuitive that a quiescent mid-plate volcano can produce such large quakes, but the detachment concept explains it. Over millions of years, Hawaii volcanoes accumulate thick piles of lava. By gravity alone, they want to spread out and collapse sideways. Episodes of magma intrusion can also inflate the flanks. These forces concentrate stress on the basal detachment fault. The detachment essentially acts as a lubricated shear zone. As the flank slowly creeps downhill toward the sea, elastic strain energy builds up until it is released in an earthquake or a series of quakes. In fact, modern geodesy shows that Kilauea's south flank creeps at a fairly constant rate on the order of 5 centimeters per year, about 2 inches per year, toward the ocean. Every few years, that slow movement speeds up briefly in a slow slip event, releasing as much energy as a magnitude around 6 earthquake, except that it happens over days and generates no shaking. These slow quakes demonstrate the detachment activity. The May 22, 2026 quake was a fast release. Its moment tensor indicates a dominantly reverse thrust mechanism, meaning the hanging wall side of the fault shoved under the footwall. The oblique component suggests the fault is not perfectly aligned with the slide direction, which is reasonable because the island contours curve. All of this is consistent with what Hawaiian Volcano Observatory geophysicists call a flank slip earthquake on the basal detachment. Crucially, there is no sign that magma or rift zone intrusion was directly involved. The United States Geological Survey emphasizes that earthquakes at this location and depth in Hawaii are due to movement along a detachment fault which separates the top of the original oceanic crust from the pile of volcanic rock. In other words, it is a structural earthquake, not a volcanic one. Hawaiian Volcano Observatory scientists were quick to point out that this kind of quake does not signal an increase in volcanic activity. It is part of the south flank normal behavior. This magnitude 6.0 shock also prompts us to remember the patterns of past sequences. The 1975 Kalapana quake was followed by years of heightened activity on the south flank. Likewise, the 2018 magnitude 6.9 quake along Kilauea Lower East Rift Zone was accompanied by thousands of aftershocks, many on the detachment. The geological record goes deeper. In 1868, the big event was preceded by a cascade of foreshocks. Frederick Lyman letters describe hundreds of little tremors in the days leading up to April 2nd, some strong enough to shake houses, culminating in a magnitude about 7.1 quake hours before the magnitude about 7.9 main shock. Modern analysis suggests that the March 28, 1868 magnitude 7.1 could itself have been a slip of an adjacent fault block, possibly the Mauna Loa southwest flank, which then shook loose the larger south flank block on April 2nd. In that sense, the 1868 scenario involved 2 separate sliding blocks. First, a smaller flank block moved, triggering aftershocks, then the huge Kilauea flank slide occurred. Could our 2026 quake be the latest chapter in a similar saga? It is impossible to say with certainty, but history suggests vigilance. We know from both 1868 and 1975 that rupture on the basal detachment can happen in pieces. A moderate event on one portion of the fault can increase stress on adjacent segments. The 1975 rupture itself involved multiple segments. Geodetic studies show that part of the detachment slipped beneath the offshore bench and part slipped under land, producing significant uplift and subsidence patterns. Similarly, after the magnitude 6.9 quake of 2018, stress transfer along the detachment may have primed other patches for release. In short, the island's southeast flank remains a complex jigsaw of blocks bounded by faults, and a shake on one piece does not rule out another. All of these quakes occur within the same structural system, the volcanic flank moving outward on a slippery base. As one Volcano Watch author noted, the big quakes of 1868, 1975, and 2018 were all rooted in the same detachment fault. They differ mainly in size and location, but the mechanism is consistent. In this event, on May 23rd, the decompressed pattern is recognizable. Our focus now is on the geology, not sensationalism. There is no credible evidence linking this quake to anything supernatural. Instead, it is a reminder that Hawaii volcanoes are not only surface lava fountains, but also deep, creeping giants. From a hazard perspective, a quake of magnitude 6 is large enough to cause damage locally, with building inspectors likely out surveying cracks in roads or walls, but much smaller than the catastrophic events of the past. It produced strong shaking near Hononau-Napupu and was felt island-wide, with over 2,000 felt reports logged almost immediately, but it did not trigger any tsunami or volcanic eruption. The immediate concern for scientists is to study the aftershock pattern closely. If the rupture truly occurred on the basal detachment, we expect aftershocks to continue as the fault plane adjusts, possibly with magnitudes approaching 5 or 6. In the decade following 1975, earthquakes up to about 1 magnitude unit below the main shock continued on Hawaii's south flank. For science enthusiasts, the intriguing aspect is watching a textbook example of geophysics in action. Instruments will monitor whether the south flank creep rate changes or whether nearby faults become more active. Researchers may deploy ocean bottom seismometers offshore to image the deep fault and detect any hidden slip. Theoretical models of slope stability and earthquake triggering will be tested against the data from this event. All signs, though, point to familiar physics: gravity-driven spreading and large volcanic loads, building up strain on a weak layer deep in the crust. When the strain exceeds friction, a slip occurs, releasing seismic waves that we felt and setting off additional motion beneath the waves that we did not feel. In the end, the message is hopeful. Hawaii hazards are well studied and largely understood through geology. No prophecy or mystery is needed, only physics and good data. This earthquake is part of a pattern we have seen before on the Big Island, one that science, using ocean-bottom seismographs, global positioning system measurements, and geologic mapping, is steadily unraveling. By studying events like May 23, we refine our picture of the deep detachment fault geometry and the stresses within the volcano. That knowledge will help improve estimates of how large future earthquakes might become, or where slow slip events may relieve stress next. Until then, what do we take away? The geology provides the full explanation. This was a flank earthquake, not a summit eruption. It reflects the long-term gravitational spreading of Hawaii volcanoes, punctuated by occasional ruptures on a deep detachment fault. It also serves as a reminder that the island deep foundations are as dynamic as its surface, and that understanding them is essential for staying safe in one of Earth's most active volcanic settings.